Okay, so this is just going to be video solutions to the independent tree diagram task from Tuesday the 7th. I'll upload the written document as well afterwards, in case you don't have time to watch this whole video. So, Helen flips a dice and flips a coin. Probability that she gets a 4 and a tails. So that is going to be this path here, 4, and then tails. Well, what's the probability of getting a 4 on a dice? That would be a 1/6. And the probability of getting a heads on a coin would be a 1/2. So to figure out this branch, we do a 1/6 multiplied by a 1/2. So a 1/6 multiplied by a 1/2 would be 1/12. So our answer is 1/12. So again, I didn't fill out the whole tree diagram. I first acknowledged what path I wanted, and it makes it a lot easier work for you. Question 2. So they're wanting us to fill the whole tree diagram in here, so we have to. So this is a biased dice, so don't have into your head 1/6 on everything. Of rolling a 6th, the probability is a 5th. We know that these must add to make 1. So add to equal 1. So 1/5, this must be 4/5. And it's the same dice. We roll the exact same dice. So it's going to be 1/5 and 4/5 the whole time. They aren't dependent on each other. That's why we call them independent tree diagrams. So it doesn't matter what happens here. It's the same probability on the second go round. So we've done that. Probability of rolling 2 6s, well, that would be this and this. So we need to do 1/5 times by 1/5. So this is 2 6s. So the probability of rolling 2 6s would be 1/5 times by 1/5. That would be 1/25. So that's our probability of rolling 2 6s. Going down and to the left for question 3. Again, a biased coin. Probability of landing on a heads is 2/7, so the probability of landing on a tails must be 5/7. Exact same coin, so I'm going to fill in the exact same probabilities down here. Complete the tree diagram. That is it. There's a weird smiley face. Done. Come on, let me scroll across. Spot on. Okay, so Sue either travels by bus or walks when she visits the shop. The probability that she catches the bus to the shops is 0.4. So first of all, let's fill in what's here. Well, that must be 0.6. Probability that she catches the bus from the shops, so the bus from the shops is 0.7. Bus from the shops is 0.7. So not taking the bus, which is just her other option is walking, must be 0.3. Because this would add up to be 1, this would add up to be 1, this would add up to be 1. So we've done that. Show that the probability that Sue walks at least one way is 0.72. So this is bus, bus. This is bus, walks. This is walks, bus. And this is walks, walks. You can see from the path, walks, then walks, walks, then bus. So if she walks at least one way, well, my options here are bus, then walks, walks, then bus, and walks, then walks. So this one, and this one. Well, to calculate bus then walks, I would do 0.4 times by 0.3. This multiplied by this. To calculate walks then bus, I would do 0.6, because that's walks, and then bus is 0.7. And to do walk then walk, I would do 0.6 times by 0.3. So if we calculate all of them, this would be 0.12, this would be 0.42, and this would be 0.18. So then just adding these up, we would hope that we get to 0.72. So 0.12 plus 0.42 plus 0.18 does in fact give us 0.72. So then we've shown it. Down to question 5 out of 7. We've got a set of cards labelled cat, dog, hamster or rat. Complete the table. Well, we know that all of these 4 would equal to 1. So we need to think, well, what goes here to make them equal to 1? So I'm going to do 0.35 plus 0.4 plus 0.1. You can put 0 there if you need to help yourself. So 5, 7, 8. Well, this must be 0.15 to make that up to 1. And I'll write that there, because 0.15 plus 0.85 equals 1. So we've done that first bit. Julia chooses a card at random from her set of cards. What is the probability that the card is labelled cat or hamster? Well, we just do the probability of cat plus the probability of hamster, because when we say or, that's kind of probability terms for add. When we say and, that's the probability terms for timesing. So that's 0.35 plus 0.1. That equals to 0.45. I got my values from up here, hopefully you can see. Julia's sister has an identical set of cards. They both each choose one card at random. What they mean by this is they have the exact same probabilities up here. What's the probability that they both choose the card labelled dog? So we might want to draw a tree diagram here. But you won't want to draw it all because it's going to get really, really messy if you do. So we've got cat, dog, hamster, and rat. Probability that they both choose dog. So we don't actually care about this path, and we don't care about these paths because that's not dog, dog. So I'm only going to fill in the probability of dog, which is 0.4. And then I would have 4 paths off here. Cat, dog, hamster, rat. But again, we don't care about these. So again, I'm just going to fill in my path for dogs. So this is dog, dog. So I just want that path. Remember, we multiply. So this would be 0.4 times by 0.4, which is 0.16. So it looks a bit messy now, but as you can see, I made that a lot simpler question than it probably could have been if you draw the whole 4-way tree diagram. Okay, final 2 questions. So, same tree diagram as we actually had in an earlier question. So this should be 4/5. We're going to have 1/5, 4/5, 1/5, and 4/5. It's the same dice. So we've filled in our tree diagram here. So we'll take that off. Work out the probability of rolling exactly 1/6. So that could be the path of 6, then not 6. And that could be the path of not 6, then 6. Because this top path would be 2 6s, this top path would be no 6s. So calculating this top path, we do 1/5 times by 4/5, which would be 4/25. And this would be 4/5 times by 1/5. So 4/5 times by 1/5, which is again 4/25. We then need to add these. So 4/25 plus 4/25 equals to 8/25. And that is our answer. And I'll put a little line there. That's the probability of getting exactly 1, 6. And then final question. This had a tricky part at the end, which I'll talk about. So a game consists of randomly choosing a bag, blah 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 blah. They filled in the majority of the tree diagram. They just haven't filled in this bit. So we need to do 0.35 plus 0.45. That's going to give me 0.8. So then I can tell, well, this must be 0.2. As we do 1 subtract 0.8. Remember, these three all should add up to 1. So we've completed the tree diagram there. Work out the probability that a player selects a red ball. Well, we can either do that through going through into bag 1 and collecting red, bag 2 and collecting red, and bag 3 and collecting red. So we've got 3 options here. This path would be 0.35 times by 0.6. I'm going to write them all out again here. This one would be 0.45 times by 0.2. And this path would be 0.2 times by 0.7. So, multiplying these, we're going to get 0.21. We're going to get 0.09. And we're going to get 0.14. We then need to add these. So that's going to give me 0.44. So my answer is 0.44. That's the probability of selecting a red ball. We just had to check it through each bag and then add up them afterwards. After we did our multiplication. The same player is going to play the game 200 times consecutively. Work out how many black balls he has. Well, you only either pick red or black. So if the probability of picking red equals 0.44, well, the probability of picking black must be 1 subtract 0.44, which is 0.56. You could have done that by doing these 3 branches as well, but I think that's that's obviously a lot simpler method. And then we're going to use a little, I don't know, formula, but it's a bit of a common sense one. Think of it logically. If you flipped a coin 200 times, how many times would you expect it to land on heads? You'd say 100, because you've done a half of 200. You've done 200 times by a half. You've done the amount of times you do the experiment times by the probability of it. So expected outcome equals number of trials times by the probability. And that's something you can kind of reason yourself if you ever forget it. So what we do need to do here, squeeze this in, is to do 200 times by 0.56. That's my probability. That's my number of trials. So if I do 200 times 0.56, well, I'm going to get, where can I squeeze this where it's not going to look disgusting? I'm going to get 112. So my answer to this one is 112. So if we did this game 200 times, we'd expect, it's not possible, well, it's not always going to come out like that. That's not how probabilities work. They're not exact sciences. We'd expect it to come out 112 times. Okay, and that's it from me. Hopefully that was helpful if you just kind of picked out the questions you wanted to look at.